This video is going to show you how to build a battery recharger for 2 AA batteries using solar cells. Before getting into the lab, we're going to look at how sunlight is converted directly into electricity. Photovoltaic panels or solar panels that you see mounted on top of rooftops are made of a material that converts light into DC voltage and current. This voltage and current is similar to the voltage that you get from a battery. Photovoltaic technology was developed in the 1950s for powering remote equipment in space, such as satellites. Today we see photovoltaics used for powering small devices such as calculators, as well as bigger things like this traffic calming sign that you see in the photo. Photovoltaic materials are most commonly manufactured with silicon crystals. Silicon has 14 protons and 14 electrons. The 4 electrons that orbit the nucleus in the outermost energy level are called valence electrons. These electrons are shared with neighboring silicon atoms through a covalent bond. Looking at the periodic table, we can see that silicon is in column 4, indicating its 4 outermost electrons. Now, suppose we have a silicon crystal and we replaced some of the silicon atoms in the crystal with boron. Boron has only 3 valence electrons. So for every boron atom, there would be a missing electron or hole in the crystal. Boron is called a p-type dopant. P because the holes in the crystal behave like positive particles. Now, suppose we took another crystal of silicon and we replaced some of the silicon atoms with phosphorus. Phosphorus is in column 5 of the periodic table and has 5 valence electrons. This would mean we would have extra electrons hanging around in the material. For every phosphorus atom, there would be a free electron in the material. Phosphorus is an N-type dopant because it contributes negative electrons to the crystal. In this picture, the top half of the crystal has phosphorus impurities in it. The phosphorus dopant makes the top half N-type silicon. Note the 4 free electrons. In the bottom half, the crystal has been doped with boron, making the crystal p-type. Note the 4 holes. The tendency now is for the electrons to move across the p-n junction to fill the holes. When the electrons move from a high concentration to a low concentration, it is called diffusion. Initially, the N-type and p-type crystals are neutrally charged. However, when electrons migrate down across the p-n junction and fill holes, an electric field develops across the junction. The electric field counteracts the diffusion of electrons. This means some electrons will remain in the N-type crystal and some holes will remain in the p-type crystal, just as you see here in the picture. Due to the electric field across the junction, electrons can only flow in one direction through the silicon. Any electron that exists in the p-type crystal will be pulled across the junction to the N-type side. Now suppose we shine light on our silicon solar cell. The sun's radiation carries energy, and some of that energy will be absorbed by valence electrons, popping the electrons out of their holes. So when photons of light hit the crystal, electron-hole pairs are formed. Due to the electric field at the junction, electrons are pulled up and holes are pulled down. Now, if we connect a load to the cell, similar to the light bulb that we see in this picture, then electrons will flow through the load to recombine with holes on the p-type side. This flow of electrons is the DC current that powers the light. Here is a cross-sectional view of a PV panel. A conductive contact grid collects the current and sends it to the load. An anti-reflective coating helps to minimize reflection and maximize the absorption of the sun's radiant energy. The entire panel is protected with a glass coating. Most owners of residential PV systems are still tied to the electricity grid. The grid is a large interconnected network that brings electricity from generating plants to consumers. In this picture, between the PV panels and the circuit breaker box, there is an inverter. This inverter converts the DC electricity produced by the panels to the AC electricity used in our homes. In this system, the PV is primary and the grid is a backup. In addition, if the power produced by the PV panels exceeds the energy demands of the home, the power meter will spin backwards. This acts as a credit on your utility bill. This picture shows a system that is not tied to the electricity grid. Energy is stored in a battery because there is no grid to serve as a nighttime or cloudy day backup. Similar to the last slide, an inverter is needed to convert from DC voltage to the AC voltage and current required by all home appliances. In addition, in this system, there is a charge controller or regulator that ensures the battery is not overcharged by the solar panels or overdrained by DC loads. Later, at the end of the lab, we will show a small system with all of these components. When constructing large PV panels, smaller panels can be wired in parallel. A parallel connection means the panels are connected across the same 2 points. A parallel connection increases current, but not voltage. A series connection means the positive side of one panel is wired to the negative side of another panel. This increases the overall voltage. The current flowing is the same in all the panels. So a series connection increases voltage, but not current. We will show both parallel and series configurations as we go through the lab. In this lab, we build a battery recharger unit using 2 solar cells and 2 nickel metal hydride rechargeable batteries. Before we get into how this unit is constructed, what I want to do first is test each solar cell to ensure I'm getting the voltage and current I expect. Now, the manufacturer of the solar cell rates these cells at 3 volts and 37 milliamps. So I'm going to use my multimeter to test the voltage and the current to see if that's what I'm getting out of each solar cell. So I'm not outside, I'm inside, so I'm going to simulate sunlight with a full spectrum light. And so I'm going to turn that on, and my camera is going to have to adjust a little bit. And so now I'm going to test each solar cell to see what voltage and current I'm getting. Okay, I've got the first solar cell connected to the multimeter, and I'm getting 3.03 volts approximately, so that solar cell appears to be working as claimed. Now I'm going to disconnect the multimeter from that solar cell, and I'm going to connect to the other solar cell in the same way and check that other solar cell to see if I'm getting approximately the same thing. Okay, I'm doing a little bit better on the other solar cell. I'm getting 3.20 volts, and that's definitely within range. If I adjust my light and make it a little bit closer, or I move it such that it's a little bit brighter on the second solar cell, you can see the voltage increase, and and if I move the light away, of course the voltage decreases. So all right, so the 2 solar cells appear to be putting out the appropriate voltage. Now I'm going to be testing the current to see if I'm getting approximately 37 milliamps.